Have you ever wondered how the food in our body converts into energy? How medicines cure illnesses? Or how fuels help in driving vehicles? Answer to all these and similar questions is a single word: chemistry. Chemistry is the branch of science that deals with the study of the composition, structure, properties of matter, and changes that matter undergoes. What is matter? Anything that has mass and occupies space is known as matter. Before we learn more about matter, it is important that we know the importance of chemistry in our daily life. It is interlinked with other branches of science and plays an important role in our daily life. How important is it in our daily life? Let's explore. Chemistry plays a major role in identifying the weather patterns, manufacturing fertilizers, alkalis, acids, salts, dyes, polymers, drugs, soaps, detergents, metals, alloys, other inorganic and organic chemicals, and new materials that contribute in a big way to the national economy. Meeting human needs in producing food, healthcare products, and other materials aimed at improving the quality of life. Producing superconducting ceramics, conducting polymers, optical fibers, and large-scale miniature of solid-state devices. Synthesizing safer alternatives to environmentally hazardous refrigerants such as CFCs, chlorofluorocarbons, responsible for ozone depletion in the stratosphere. Understanding biochemical processes and the use of enzymes for large-scale production of chemicals, and synthesizing of new materials, which have extensive uses in various fields. Of chemistry in different fields and benefit from it, it is important that we know about matter. Based on the arrangement of the constituent particles, matter can exist in three physical states: solid, liquid, and gaseous. Let's look at the description of each state along with their characteristics. In solid state, the particles are held very close to each other in an orderly fashion. Hence, there is not much freedom of movement. They have definite volume and definite shape. In liquid state, the particles are loosely held together and can therefore move around. They have definite volume but no definite shape. they take the shape of the container in which they are placed. In gaseous state, the particles are far apart as compared to those present in liquid state. Therefore, their movement is easy and fast. They have neither definitive volume nor definite shape, and they occupy the available space of the container in which they are placed. The three states of matter are interconvertible by changing the conditions of pressure or temperature. For example, on heating, a solid changes to liquid. Liquid, on further heating, changes to gaseous state at normal atmospheric pressure. Similarly, in the reverse process, gas on cooling changes to liquid, and on further cooling, liquid changes to solid. Matter can be classified as pure substances and mixtures based on the chemical composition. Substances which contain only one kind of atoms or molecules are called pure substances. And in a pure substance, the composition of a substance is fixed. For example, carbon dioxide is a pure substance which consists of only molecules of carbon dioxide, and it has carbon and oxygen in a fixed ratio. When elements or compounds are mixed together in any proportion, it results in the formation of a mixture. Thus, in a mixture, the composition varies. For example, seawater comprises of dissolved salts and water. The seawater consists of varied amounts of dissolved salts and water. Pure substances can be further classified into elements and compounds based on separation of it into its respective constituents. Substances which consist of only one kind of atoms are called elements. Examples of elements are sodium, copper, silver, hydrogen, oxygen, etc. An element cannot be further separated into its constituents by physical or chemical means. For example, oxygen consists of only oxygen atoms, and it cannot be further separated into its constituents, that is, oxygen atoms. Two or more elements combine chemically in a fixed proportion to form a compound. Examples of compounds are ammonia, water, etc. A compound cannot be further separated into its constituents by physical means, but can be separated by chemical methods. For example, oxygen and hydrogen are present in a 1:2 ratio by volume in water, and water, that is H2O, can be separated into its constituents, hydrogen and oxygen, by electrolysis, but cannot be separated into its constituents by any of the physical methods such as distillation, fractional distillation, etc. Also remember that the properties of a compound are different from those of its constituent elements. For example, the elements hydrogen and oxygen, being gaseous in nature, combine to form a compound, water, which is a liquid. Mixture can be classified further based on the uniformity of the particles present in it. If the particles are distributed uniformly throughout the solution, then it is a homogeneous mixture. For example, sugar solution is a homogeneous mixture because sugar particles get distributed uniformly throughout the solution. If the particles are not distributed uniformly throughout the solution, then it is a heterogeneous mixture. For example, sand dissolved in water is a heterogeneous mixture because sand particles are not uniformly distributed throughout the solution. A mixture can be separated into its constituents by physical methods. For example, a mixture consisting of iron filings and sulfur powder can be separated by using a magnet, that is, by magnetic separation. As we learnt, matter is anything that has mass and occupies space. Every substance is made of matter and has unique properties. We can classify properties as physical and chemical properties. Let's learn about them. We have with us a rubber ball. Let's see how we can describe it. By looking at and feeling the ball, we can see that the ball is a solid. It is round and yellow in color. It smells like rubber and it bounces. Now, let's observe this block of sulfur. We can say that sulfur is a yellow solid crystal and has a strong odor. What we saw are the physical properties of a rubber ball and sulfur. These properties can be easily seen or felt. Thus, we can say that physical properties are those properties that can be measured or observed without changing the identity or the composition of the substance. Color, length, mass, area, texture, elasticity, odor, melting point, and boiling point are examples of physical properties. Physical properties help us describe a substance. However, the description is not sufficient to identify a substance. For example, saying that sulfur is something that is yellow and solid and has a strong odor is not enough, because there can be many solids that may have the same properties, including our yellow rubber ball. Hence, it is necessary to also know the chemical properties of a substance to identify it correctly. The chemical properties of a substance can be observed when a substance undergoes a chemical change. Flammability, reactivity to an acid, and reactivity to water are examples of chemical properties. For example, if we burn sulfur, it produces a blue clear flame. Thus, the blue clear flame is a result of chemical property. When performing a chemical experiment, scientists study the properties of substances. This involves measuring the quantitative properties of a substance. Let's see. If we have few grains of rice scattered in the plate, we can easily count them and say that they are 20 in number. However, what if we were asked to count the rice grains in this bowl? We would count them, but due to the large quantity, we may not be able to confirm if our count is accurate. One way of ascertaining the accuracy of measurement is to repeat it. Let's assume that we know that there are 105 grains in the bowl. Thus, the correct value of measurement is 105. Now, let's say we ask 4 people to count the grains, each 5 times. Shown here is the data of each person. We know that the correct value is 105. If the average value of one of the measurements is close to the correct value, then that measurement is said to be accurate. If the values of measurements are close to each other, and hence close to their average value, then the measurement is said to be precise. Let's look at the data to understand what it shows us. For person A, the average value matches the correct value. Also, the values of different measurements are close to each other. Hence, we can say that A's data is accurate and precise. For person B, the average value is not close to the correct value, but the values of different measurements are close to each other. Hence, B's data is not accurate, but it is precise. For person C, the average value matches the correct value, but there is a variation between the values of different measurements. So, C's data is accurate but not precise. Note that accuracy without precision could be a matter of chance. For person D, the average value does not match the correct value. Neither are the values of different measurements close to each other. So, D's data is neither accurate nor precise. The certainty and uncertainty in a measurement is indicated through the use of significant figures. Significant figure is the total number of certain digits in a number, including the last digit whose value is uncertain. The uncertainty is indicated by writing the certain digits and the last uncertain digit. For example, if a measurement is reported as 16.3 ml, we can say that the 16 is certain and 3 is uncertain, and the uncertainty would be plus or minus 1 in the last digit. Let's see the rules to determine the number of significant figures in a reported quantity. The first rule says that all non-zero digits are significant. For example, 897 has 3 significant figures. 0.23 has 2 significant figures, and 9.87 has 3 significant figures. According to the second rule, zeros preceding the first non-zero number are not significant. Such zeros indicates the position of decimal point. For example, 0.0325 contains 3 significant figures. The third rule is zeros between 2 non-zero digits are significant. For example, 5.01 contains 3 significant figures. The fourth rule is all zeros placed at the end or to the right of a number are significant, provided they are on the right side of the decimal point. Therefore, 0.400 has 3 significant figures. However, terminal zeros are not significant if there is no decimal point. For example, 100 has only one significant figure. The fifth rule says that the exact numbers or numbers that are obtained by counting rather than measuring are assumed to have infinite significant figures. For example, 8 apples have infinite significant figures, as 8 is an exact number and can be represented by writing infinite number of zeros after placing a decimal, that is 8.000000 infinitum.